So another way we could have looked at this problem last time is drawing a tree. Right? Either you have a 4 or you don't. 1/6 chance of getting a 4, 5/6 chance of not getting a 4. And then there's second roll, again, 4 or not, 5/6 chance of not getting a 4, and then third roll, fourth roll, fifth roll. We want to end up here. So how do we end up in this spot here? We multiply all these numbers here, right?
Right.
So we end up with 5/6 to the 5th power. Perfect. Now, this one, 14 boys and 8 girls on a bus. What's the probability to pick at least one girl? So here, instead of finding at least one girl, you do 1 minus probability of, and again, this one, at least one, instead you're going to write the word none, and then write the rest of it. None what? None girl. So 1 minus probability of no girls. So for a second, let's figure out what the probability of no girls is. So this part here, we're going to do off to the side. Probability of no girls. What's the probability? The first one is not a girl.
14 out of 22.
Yep, 14 out of 22. There's 14 boys out of 14 plus 8, 22 people. 14 out of 22. After you choose that one, what's probably the second one is not a boy, and not a girl, sorry. Yeah, so now we only have 13 left that are not a girl. And we only have how many people, kids left? 21. So we need the first one to not be a girl and the second one to not be a girl. And we multiply. So you're going to multiply those. What do you guys get for that?
You're missing one, aren't you?
Oh, 3, I'm sorry. My bad, thank you. And then the next one?
12 out of 20.
12 out of 20. Perfect. So you multiply those, what do you get?
2184.
What?
Okay, wait. So here we got 2, here we got 3.
Oh, my so final answer is 0.
And then there we have 4. And then there we have 1 and 11. Sorry. Is that right? So, and then we have, this becomes 10 and this becomes 1. So 13 over 110?
That's
What did you guys get? What was that?
13 out of 55 is 0.2.
Oh, it's 55?
Wouldn't it just be
Wait,
easier to
what?
divide it when it was...
Well, what's,
Divided
okay,
by
just
9.
tell me what the answer is.
236.
What was that?
0.236.
236?
Yes.
Oh, it is over 55 then, for sure, because it can't be. Okay. I don't know what I screwed up. I screwed up something along the way.
Because you didn't times the 13 times.
Oh, this is, I don't know. All right, so here we have, oh, I know why. This is still 2.
0.7.
So we want to do 1 minus that, right? So then we go, take this part. This is sort of like think of this as sort of a sidebar kind of in a way. Or I don't know if that's the right word, but whatever. And then we're going to continue on down here, and we're going to do 1 minus 0.236, 0.7564. Good? Everybody on board?
Yeah.
Okay. Perfect. I'm going to skip figuring out how to do the formula. Okay, so here's another thing we need to cover just quickly. So let's get, yeah, Noe?
I would get a question on the previous one.
Yeah.
How come on that one, after we multiplied all of them, we subtracted it from 1, and on the previous question we didn't?
We did. At least one?
No, but
We subtracted from one.
yeah, but on the top one with the dice, we didn't.
This is, oh, this one?
Yeah.
Because it's not at least one. Do you see at least one there? It says no fours, not at least one. At least one. No fours is easy. So again, the no's and the alls, you just calculate those. That's a piece of cake. Because no is no, 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 no. All is yes, 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 yes. Yes, whatever, how many yeses you have.
No,
It's the at least ones that you have to subtract from 1. So this part up here, is that what you're talking about?
no, I meant like theoretically, part B on number 6 is almost the same question as number 7, right? It's both asking for the same thing. It's asking for at least 1.
We did the same thing. You see the bottom, it says 1 minus 0.42.
Okay.
See where it says at least 1 4?
Yeah, never mind.
It's right here.
Yeah, I see that.
Yeah,
My fault.
so we did there. Yeah. Cool. All right, good. So I'm glad. See, it took like 30 seconds and now you're totally on board.
Yeah.
Good. Yeah, so definitely ask those questions so that we don't get confused along the way. I'll keep things cleaner. Okay, good. So how about Clayton? Go ahead and read for us.
If you are choosing 3 out of 6 from one category, appetizers, and 3 out of 5 from another, entrees, then find out how many combos are your choices for the first option and how many combos for the second option, and then you use fundamental for the combos.
Perfect. So for example, we're planning a party, and the caterer says, oh, you get to pick 3 out of these 6 for your appetizers, and we'll serve those 3 appetizers at your party. So picking 3 out of 6, does order matter? No, so it's just going to be 6, choose 3. Everybody kind of on board with that? Good. So this will be 6, choose 3. And then they say, oh, you need to pick out 3 out of 5 entrees for your party. Again, order doesn't matter. So that would just be 5, choose 3 for the entrees. So appetizers, 6, choose 3. Entrees is just going to be 5, choose 3. But because you need to pick this one, this will tell you how many different kind of appetizer choices you have, or appetizer combinations you have. And this tells you how many entree combinations you have. But for every appetizer combination you have, you get all the different possible entree combinations. So your total outcome, fundamental accounting principle, is number of choices for the first thing times number of choices for the second thing. You'd multiply those two together. Here, I'll show you what I mean. So this would be 6, choose 3, and this would be 5, choose 3. That'd be your total outcomes. So, for example, so think about them as boys. So I have these 6 boys here. I need to pick 3 of them, right? I could pick these 3, I could pick these 3, I could pick those 3, I could pick those 3, right? I have all these different ways of picking 3 of them. I also need to pick out of these 5 girls here, I need to pick 3 of them. There's a bunch of ways of picking those 3 girls. But for every combination, I can pick these 3 boys, I still have a whole bunch of combinations of picking these 3 girls. And then I pick, instead I pick these 2 boys and that one, I still have all those combinations of picking these 3 girls. If I pick those 3 boys, I still have all these different combinations of picking these 3 girls. So how many ways do I have of picking these 3 girls? I take that many, and how many different times can I do that? As many times as I pick 3 boys out of these 6. So it's kind of like this giant tree you can think of. Right? For every way there is of picking 3 boys, right? This is pick 3 of 6 boys. There is all the different ways of picking 3 out of 5 girls. How many of these am I going to have? As many as there are ways of picking 3 boys. So how many options will there be? There'll be the number of ways of picking. This is pick 3 of 5 girls, right? How many? If there's 10 of these, How many groups of 10 are there going to be? 3 choose 6. Actually, what is 3 choose 6? So 3 choose 6 is going to be, sorry, my bad. 6 choose 3. Thank you. It's going to be 3 spots. 6 times 5 times 4 divided by 3 times 2 times 1. It's going to be 20. So it's going to be 20 of these different spots here. For every one of those 20, I'm going to have 5 choose 3 girls. 5 times 4 times 3 divided by 3 times 2 times 1. 10. I'm going to have 10 possibilities. So I'm going to have 10 off of here. I'm going to have 10 off of here. Right, so there's 10 here. How many groups of 10 am I going to have? 20 of them. So 200 possibilities. Is that everyone kind of following?
Yeah.
Okay, good. So that's just kind of the extra step we kind of look at. What if I was going to add in also 2 out of 4 desserts? What would that be? So here I've got 6 choose 3 times 5 choose 3. What would be and then what?
4 choose 2.
And then 4 choose 2. We'll multiply that by 4 choose 2 because every one of those 200 possibilities for my meals, now I have 4 choose 2 possibilities for my dessert. Good so far? All right, so you're not going to get tested on this part, but I did want to cover it because it is interesting. Okay, so this is how you figure out which counting method to use. So first of all, if you're going to replace things, then you just use a regular fundamental counting principle. Like me pulling out and picking a 4-digit pin, right? You can reuse numbers. Or if they're not even in the same category. So it's like shirts and pants and socks. There's no overlap at all. So of course you're not going to, you don't need to worry about replacing because they're not overlapping at all. So both those situations use the fundamental counting principle. But when you have a big group, big pool that you're drawing from, that you're choosing from, like a giant pool of students or a giant pool of puppies, you're going to pick a puppy and you're going to pick another puppy and you're going to pick another puppy. Or students, you're going to pick 3 students and you're not going to reuse them. You can't reuse items. Then that's when you use a permutation or a combination. Right? When you have race horses and one comes in first, second, and third, the same horse can't come in first and second and third. That's when you use a permutation or a combination. Permutation would be if order matters. If you're picking them and you're putting them into a particular spot. Combination is when you're going to pick them and you're going to throw them into a bin and they're all going to kind of roll around and it's chaos and order doesn't matter. So this one, because it's chaos, that's the unusual one. You have to divide. You have to do the dividing by part. It's the unusual one. It's the exception. And then that one, we didn't really cover that one, so I'm not going to worry about that too much. That's kind of what I was talking about a second ago. All right. Before we do the summary, I brought in some truffles. Linder truffles, these are really good. But there's not enough for everybody, so to make it fair, if you flip over a red card, you get a truffle. If you don't, then you don't get a truffle. So the first 10 people up here, or first 6 people up here get to draw. So come on up. We'll do 6 at a time. So let's get 6 people up first. 2 more people can take a shot at it. 1 more person can take a shot at it. Yep. One of you, go. Okay, go ahead and draw. Oh, sorry, I gotta change it. Okay, I'm gonna put it back in. Hold on, let me stick it back in here. You can draw from anywhere in the deck you want. Anywhere in the deck you want. Okay, so anywhere in the deck you want. Oh, You guys are terrible drawers. Okay, go ahead. All right, one last person. All right. So I guess my question to you is, who thinks that I have a rigged deck? You guys. All right. So first, let's assume that my deck is a normal deck. Okay, so this is what we call hypothesis testing, which we're going to get to later on in Chapter 8. The null hypothesis assumes that my deck is like everybody else's. Right, so null hypothesis assumes that yours is the same as everybody else's. If that's the same as everybody else's, what's the probability? What proportion of cards would be black? Half. So we're going to assume that my proportion is 50%. Does that make sense? 1/2. So we're going to assume that mine's the same as everybody else's. Then we did an example. We did a sampling. How many people drew? The first person, we had 6 people draw. Is that right? So the first person, what's probably they draw a black card?
50%.
50%. Second person who drew, what was their probability of drawing a black card? Same, because remember we replaced it each time? The next person, what was their chance of drawing a black card? Next person? Next person? Yep, and we had 6 people. So the first person and the second person and the third and the fourth and the fifth and the sixth all drew black cards. And we multiply. So multiply these all, we end up getting 1/64, which is like maybe 1.5%? Anybody? 1.5%? 1.6? Okay, 1.6%. What's our guideline for unusual again?
Less than 5?
Yeah, 5% or less. Is this unusual?
Yeah.
So is it more likely that we just got unlucky, 6 people got really unlucky and picked black cards, or is it more likely that my deck is a fixed deck?
Second.
Yeah, it's more likely we kind of feel like it's more likely my deck is fixed than 6 people got unlucky. So what we do is, this is exactly what we do. We make a hypothesis that our deck is the same as everybody else's, and then we take a sample. If our sample is unusual, and this sample is unusual, right? Black, 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 black is unusual. If our sample is unusual, then we would reject the null hypothesis and say that our deck is not the same as everybody else's deck. It's different somehow. So that's kind of the basic idea of a hypothesis test, because this is less, or unusual. This is unusual. Right? So that's the basic concept. Null hypothesis. First you assume that your deck is the same as everybody else's. Take a sample. If your sample is unusual, then you reject the null hypothesis and say that ours is not the same as everybody else's. Ours is different.
Are you saying no?
Null hypothesis. Null meaning like, null means none. Yeah. Okay. Cool. I kind of wanted to go over that because it's good. It's a good spot for you guys to just get a good glimpse of the future. Let's go ahead and take a look at a quick summary of things. All right.
Tell us if it's rigged.
Well, it might not be rigged. It could be that it's just unlucky, right? It's a possibility. We think it's more likely that it is rigged. You don't really know in real life. That's the thing about statistics, is you never really know for sure. It seems like there's a very, very good chance that that is a fixed deck. It might be it's probably a fixed deck. It might not be. Like if you go to the casino down the road where I used to work, it's 50-50 whether you get banker player, and you will literally see times where there are 8 players or 8 bankers in a row. Really unlikely, but it'll happen. And over the course of the evening, it'll happen at least a couple times a night. There's like 7 tables going, and there's tens of thousands of hands being played out over the night, and there'll be at least a couple times where there's 8 or 9 bankers in a row. For sure it happens. So it seems unlikely that my deck is a regular deck. Yeah, I would say that. Okay, so let's take a look at, and that's the thing that, like, I got through, like, math, all through math, life is definite. Like, you get an answer, and that's the right answer, and it's done, right? The problem with probability is everything's a little bit, nothing's for sure. Like, it's all probabilities. It's like, that's the problem with poker, is you could be 99% likely to win the hand, but that doesn't mean you're going to win it for sure. There's still that bit of chance involved. And some punk will come along and take that 1% chance and beat you, and you're just like, you're so freaking lucky. It's just so wrong. But, and then you call your friends and you complain. But, it's just, it's everything's uncertain. There's a little bit of uncertainty. So it's probably fixed. It's a really good chance it's fixed, but maybe not. Okay. And means multiply. Why? So for example, think about getting tails, 1/2 chance of getting tails. Rolling a 4, there's a 1/6 chance of rolling a 4. So probably you roll a 4 and you get tails, and it's just this part here where they overlap. It's one spot out of 12, 1/12, 1/2 times 1/6, or you can think of it as 1/6 and half of that will be tails. Half of those will be tails. And means multiply. Just remember that if they're dependent, that means you have to multiply the probability of the first one times the probability of the second one given the first one has happened. Right? So it's that tree thing, which we're going to do one of those in a little bit. Or means add, and then subtract the overlap. So everybody say or means add.
Or means add.
Say that to yourself 10 times every night for the next 5 days. So again, this one, the probability we get tails, 6 out of 12. Probably we roll a 4, 2 out of 12. But we have to subtract the overlap, the 1/12. So 6/12 plus 2/12 minus 1/12, 7/12 chance of getting a tails or a 4. You can kind of see that there. To find the probability of at least 1. So this is at least 1. If I want to find that, instead of finding all of those and adding them up, it's much easier just to find this one and subtract from 1, because we know that if I add up all of these, they're going to add up to 1 or 100%. Much easier to find the none and subtract from 1 than it is to find all of those and add them up. So just kind of remember that. At least 1 is the complement of none. Either I have at least 1 sibling, or I have none siblings, right? I know bad English, just roll with it. All right, so why don't you guys work on questions number 1 through 3 first, and then we'll go over those.